Well, thank you so much, Chris and Alyssa, for those introductions. I am so glad to be virtually here with you all today and want to start by thanking Alyssa and Chris and all the organizers for the hard work that has gone into enabling this event to go forward in this Zoom format, as well as all of you who are joining from all over. It was really great to see in Alyssa's poll that people have taken advantage of this Zoom format to be joining us from all over the US and all over the world. I also wanted to start by acknowledging that coming to you here from Boston, I live and work on the ancestral and unceded land of the Massachusetts people. And for me, as a white climate scientist and oceanographer, it's really important for me to acknowledge the role of settler colonialism in contributing to the global climate change that we're experiencing today and that I'm going to be talking about. It's also really important to center the disproportionate impacts of climate change on Indigenous, Black, and Brown communities, and the leadership of those communities in addressing the problems that I'm going to be talking about today as we discuss the ocean's role in global climate change. And so taking a step back, I want to build on this introduction that Chris gave and give us an overview of how I think about the climate system on Earth broadly. And key bringing in that air component is that carbon dioxide is an atmospheric gas that acts like a heat trapping blanket around our planet. And so for the past 800,000 years, the level of carbon dioxide in our atmosphere have gone both up and down over time. And records of past climate have shown that global temperatures have risen and fallen in concert with these changes in atmospheric carbon dioxide. However, when we burn fossil fuels for energy, we add more carbon dioxide to the atmosphere. And so what this is doing is it's thickening this heat trapping blanket around the planet to something we can think about as being more like a really thick down comforter. And so this is disrupting the Earth's climate as these carbon dioxide levels have been increasing. And so now today, these carbon dioxide levels have reached over 400 parts per million, where this number I pulled just this morning is the most recent number published just from 2 days ago. So this has led to a rise in global mean temperatures and resulting effects of climate change, such as increased incidence of heat waves, wildfires, hurricanes, and coastal flooding that I'm sure all of you have seen in the local news. And so in my work as a climate scientist, I'm really seeking to both understand and predict the future trajectory of climate change so that we can mitigate and adapt to these changes and reduce the harms that climate change is causing already to people and to society. And so often when we talk about climate change, the conversation really focuses on the atmosphere and on carbon dioxide in the atmosphere. But the oceans play a really important role in absorbing that atmospheric carbon dioxide and playing a critical role in moderating the Earth's climate. And so this really lovely animation of sea surface currents on this globe illustrates the way I think about the ocean's role in the global climate system as the heart of our Earth's climate, circulating not only heat, but also moisture, nutrients, and carbon throughout the globe. And so to put an even finer point on it, when we talk about this idea of global warming, what we're really talking about is actually ocean warming. This figure shows the warming of the surface ocean over the 4 decades from 1971 to 2010. And we can see that nearly the entire ocean is in these red colors, showing that the average temperatures of the surface ocean have been rising over time. This effect of warming is actually even more pronounced when we calculate the amount of heat that has actually been absorbed by the global oceans, calculated based not just only on temperature changes in the surface ocean, but throughout the entire water column, even kilometers below the surface. So just like you might have observed if you've been boiling water to make tea or pasta, it takes a lot of energy to raise the temperature of water, much more than it takes to warm the atmosphere. And so as a result, we find that the ocean currently absorbs 90% of the heat that's accumulating in the Earth system due to anthropogenic climate change. We can then return to this idea of the ocean as the heart of the Earth's climate system and consider also the role that the ocean plays in absorbing carbon dioxide from the atmosphere. And so to do this, I'm now showing you a figure from the Global Carbon Project illustrating modern human carbon emissions from 1900 all the way up until today. And so we can see these gray and brown wedges showing fossil fuel carbon emissions and land use changes that have been adding carbon to the atmosphere each year. And the rate of these emissions, or the rate of these human carbon emissions, has also been accelerating over time. But that's not the whole story. We also want to think about where these carbon emissions are ending up. And so we often focus primarily on this light blue wedge at the bottom, which is the carbon that remains and accumulates in the atmosphere, which, as I described earlier, has been leading to this rise in atmospheric carbon dioxide concentrations over the 20th and now into the 21st century. However, this increase in the atmospheric carbon dioxide would be much more rapid were it not for the large amount of carbon that's being absorbed both by the land and by the ocean. And so in my work as an oceanographer, I focus in particular on the ocean carbon sink, which is absorbing about a quarter of our current anthropogenic carbon emissions. And so in trying to better understand this ocean carbon sink, an important consideration is that the ocean absorption of carbon from the atmosphere isn't evenly distributed across the globe. There are regions that are shown in blue on this map that are strong sinks, absorbing carbon dioxide from the atmosphere, but there are also these regions in orange that are actually sources emitting that carbon back to the atmosphere. And so this figure is representing both the background flux patterns or exchange rates that we would have found in the pre-industrial era without adding in anthropogenic carbon emissions, and then with these human or anthropogenic carbon emissions added in over top. And so it's really important that we monitor this ocean carbon sink to understand its role in regulating the global climate system today, as well as improve our predictions of how this ocean carbon sink might change in the future. So I've now introduced to you two key ways in which the ocean has really what I would think of as a good news role in global climate change by absorbing both the heat and the carbon that would otherwise accumulate in the atmosphere, so slowing the rate of rising atmospheric temperature and carbon dioxide concentrations. However, unfortunately, there's a bad news side of this as well, which is that the heat and the carbon that the ocean is absorbing are also driving ocean changes. So rising ocean temperatures can have a detrimental effect on marine ecosystems that are not adapted to these warmer temperatures. And rising ocean temperatures also creates conditions that enable stronger and more damaging hurricanes to develop, like we've been seeing in the news throughout this entire late summer and fall hurricane season. The warming ocean is also driving rising sea levels because warmer water actually expands. And so this is already causing flooding and erosion in frontline coastal communities, such as this location in Kivalina, Alaska, that I've shown here on the slide. Now, in addition to the warming and sea level rise, we can also think about the ocean change size of the ocean taking up that carbon from the atmosphere. And as the ocean absorbs that extra carbon dioxide, it forms carbonic acid when it dissolves in water, which is increasing the acidity of the oceans. So this is already affecting sensitive marine organisms, such as this image of a dissolving pteropod that's shown here, and also poses threats to commercially and culturally important species, such as oysters and other shellfish. So in order to really monitor these ongoing changes, both to understand the climate services that the ocean is providing, as well as better understand and predict these changes that are unfolding, my research seeks to better understand what's going on in this ocean carbon sink. And so in order to do this, we really have to get under the hood and understand the individual biological, chemical, and physical mechanisms that enable the ocean to absorb carbon from the atmosphere. And so a lot of my work focuses on the mechanism on the left, which is known as the biological pump. And this all starts with phytoplankton in the surface ocean, which I was glad to hear Chris mention in his introduction. So phytoplankton, we can think of as being like the plants of the ocean that are going to do photosynthesis and transform carbon dioxide into organic carbon. Just like the plants in the ocean, they use light and nutrients to do this process of photosynthesis using a pigment called chlorophyll that makes them green. And so some fraction of the carbon dioxide that's turned into organic carbon is then going to be recycled in the surface ocean as those phytoplankton are food for zooplankton and for higher trophic levels, as well as be consumed and respired by bacteria. But some fraction of that organic carbon produced by the phytoplankton is going to escape being consumed and respired and sink out into the deep ocean, where it can be sequestered or stored away from contact with the atmosphere on timescales from months to centuries. Now, in addition to this biological process, chemistry and physics also play a really important role, where colder waters are more soluble or can absorb more carbon dioxide gas from the atmosphere. So those waters in the surface ocean that are cold with higher solubility for carbon dioxide can then be subducted into the deep ocean by physical circulation and again stored away from contact with the atmosphere on timescales from months to centuries. So my research group uses a range of methods and data sources to really address two key questions about this ocean carbon sink. First, we want to measure this how much question. We want to know how much carbon the ocean is absorbing by each of these chemical, physical, and biological processes. But knowing how much isn't enough if we can't also answer the really important question of why. And we need to know why to enable us to mechanistically predict how the ocean carbon sink will respond to ongoing global climate change and ultimately serve as an important feedback mechanism on those future changes. So I've shown on this slide here a whole range of different approaches, both biogeochemical measurements and analysis of global data sets that I use in my research. And today I'm going to focus on one story about biogeochemical measurements from autonomous platforms, like these shown on the top right, and how using these measurements is increasing our capacity to measure carbon cycling in hard to sample ocean regions and can improve our understanding of this ocean carbon sink. And so my work recently has been using a lot of data that comes from this Ocean Observatories Initiative funded by the National Science Foundation. And so the Ocean Observatories Initiative is a series of arrays of both moored and mobile platforms with co-located autonomous sensors measuring biogeochemical and physical properties. And so these are really exciting in that we've put this set of autonomous sampling platforms, both buoys like the one shown in the middle, and these mobile underwater vehicles like the one shown on the top right, in a lot of these places in the high latitude North Atlantic, North Pacific, and Southern Ocean to help us get insights into what's happening in these places that are hard to go out to in ships throughout the full year. And so I'm going to tell you in particular today about some of my work that's been focusing on the subpolar North Atlantic Ocean. And I'm particularly interested in the subpolar North Atlantic Ocean because of this large spring of phytoplankton bloom that's illustrated here in this really lovely animation of satellite ocean chlorophyll. So we can see this seasonal greening up of the North Atlantic every spring. And so we know from past work that this spring bloom drives significant biological carbon export during that productive season. But the question that I'm really interested in answering is how much of that carbon is ultimately being stored away from the atmosphere on climate relevant timescales. And so in order to do this, I've been looking at these autonomous measurements coming from the location that I've shown here in the pink star in the subpolar North Atlantic between Iceland and Greenland. And so in order to think about what's happening in this high latitude region, we have to think about the interactions between biological and physical processes. And in addition to the biology being really exciting in this region, the physics in the subpolar North Atlantic also has a really strong seasonal cycle. And in order to understand this, we have to think about the fact that the ocean is divided into a series of layers based on density. This is actually an image of the kind of experiment that I do to illustrate that with my undergraduate intro oceanography students, where you can dye different waters with different food coloring. And we can see that warmer, less dense water floats on top of the colder, denser water below. And so in the context of what we see in the ocean, that warmer layer on top is going to isolate the layers below from contact with the atmosphere and prevent them from exchanging their carbon with the atmosphere. So there's one layer at the surface of the ocean, this mixed layer, that's going to actually be the layer that exchanges carbon with the atmosphere, and layers below are able to trap carbon within them. And so we can see that the depth of this mixed layer varies throughout the year, where in spring and summer, the mixed layer is shallow, the ocean is well stratified when wind speeds are slow and atmospheric temperatures are cool. But then when the wind speeds pick up in winter and the atmosphere cools, that mixed layer can deepen down to greater than 1,000 meters in winter. And so if we think about how the biology is interacting with this seasonal cycle in the physics, we know that we have these phytoplankton in the surface ocean photosynthesizing, converting carbon dioxide into organic carbon during this part of the year that the ocean is well stratified. And some of those phytoplankton particles, the organic carbon, sinks out into the deep ocean. But that's not the end of the story, because as those particles are sinking through the water column, they're actively being consumed and respired by heterotrophic organisms. And so then when this mixed layer deepens in winter, we entrain that respired carbon back into the mixed layer and ventilate it back to the atmosphere. So unless that sinking organic carbon penetrates below the wintered ventilation depth, or the deepest layer that's in contact with the atmosphere each year, it's not actually going to be stored long term. And so in order to understand this process, what I'm really interested in doing in my work is understanding the total amount of biologically sequestered carbon each year, as well as getting into that why question and looking at the balance between how much carbon is seasonally exported each summer, and then how much of it is ventilated each subsequent winter. And so the tool that I use to do this are measurements of dissolved oxygen. And this Ocean Observatories Initiative program is really exciting because it's providing us our first opportunity to have oxygen measurements throughout the full water column and throughout the full seasonal cycle in this region, using oxygen as a tracer to tell us about the balance between net photosynthesis and net respiration. So recent work that I've been doing, funded by the National Science Foundation, has been going out to this location in the North Atlantic where we did field work at this array in the summers of 2018 and 2019 to deploy autonomous underwater vehicles that allow us to collect more accurate oxygen data, like this vehicle shown here on the left, that's ultimately allowing us to close that carbon budget and better understand this ocean carbon sequestration long term. So before I conclude, I want to come back to the summary of the good and bad news about the ocean's role in global climate change. So while my research is helping us to better understand how these ocean climate services and ocean changes are happening today and predict how they will unfold in the future, it's also really important that we pay attention to the fact that climate change is already a serious crisis and it's already causing harm to people today. So it's easy and tempting to feel a sense of despair in the face of these ongoing changes. And as a result, the question I am asked most frequently when I talk about climate change is what gives me hope in the face of this crisis? But to draw on a lesson really beautifully articulated by climate scientist Dr. Kate Marvel, hope is really the wrong question. She writes, "The opposite of hope is not despair, it is grief. Even while resolving to limit the damage we can mourn, we need courage, not hope." And so I will say that what gives me courage is the example of the current generation of new climate leaders who are providing inspiration, ideas, and solutions for how to address the climate crisis, including many of the voices in this really fabulous new book, All We Can Save, edited by Drs. Ayanna Elizabeth Johnson and Catherine Wilkinson, which is actually currently on my bedside table. I also included this map of the United States showing that across nearly the entire country, only about 35% of adults even occasionally discuss climate change. And this is a problem because key to gathering the courage and motivation to take action is this first step of even having conversations about the problem. So I wanted to leave you with a reminder that the choices we as a society make today will dramatically influence how climate change unfolds over the 21st century. This figure shows the 4 scenarios used by the Intergovernmental Panel on Climate Change in their last assessment report to project how climate change might unfold going forward, depending on choices about the rates of human fossil fuel emissions. And these scenarios lead to dramatically different outcomes for climate and ocean change, shown here for sea level rise and ocean acidification. So even though some of these consequences are going to happen no matter what choices we make today, we can still influence which of these climate and ocean change pathways humanity will choose to take. And so with that, thank you. And I'm looking forward to answering some of your questions.
Thank you, Hilary. Fantastic presentation to get us going. I fully agree with you that we have a wonderful new generation of young scientists and young sensitized people who are ready to, I think, deal with a lot of these issues that you brought up. So I think it is important to not be too depressed about where we're headed, because I think there are things that we can think about doing collectively together. We had a lot of questions coming in. I think we can move some of them to later, but we can certainly try and address a couple of them now. And perhaps in the spirit of what I was just mentioning, there's a question about what, in your opinion, would be the actionable steps that we could take to ameliorate rising ocean temperatures and biodiversity losses as individuals, let's say.
Yeah, so I know, first of all, I'll point ahead to particularly for biodiversity. Some of that will come up in Randy's talk coming up next. But I think one of the things that I often see framed as a dichotomy in talking about approaching the climate crisis is whether we should focus on individual action or on collective action. So I think it's really important to acknowledge that some of these changes require coordinated collective action. So the kinds of things you contribute to by voting, by choosing our elected leaders, and by supporting the kinds of policies that are going to lead to coordinated statewide, national, and international action. That doesn't mean that it's not also important to make choices in your own life. And I think everyone has different capacity to think about which kinds of choices you can make. Some of those choices are about mitigation, so reducing the amount of carbon emissions, so focusing on our carbon footprint. And some of those choices are about adaptation. And the thing that I would highlight as being really important here is when we think about mitigation and adaptation, we want to really think about the needs of these frontline communities. And so think about how we highlight a just transition from the fossil fuels we're using today to carbon neutral economy in the future, and think about how we can accomplish that in a way that centers the needs of the people who are already being most affected and have contributed least to the problem, who are tend to be our Indigenous, Black, and Brown frontline communities.
Great. Do we have time for one more question? Perhaps we can, a more directed question. You showed very nicely how biology, together with physics and chemistry, everything participates in bringing carbon dioxide into the ocean, and we see the intricacy of the Earth system, in that biology is an intricate part of the physics and chemistry, which is not always appreciated, which we often forget. So it was very nice that you showed that very nicely in your talk. Could you just give us an idea of how important is the biology for the carbon pump into the ocean? compared with the physics and chemistry, and how important is the ocean compared to land, photosynthesis in plants and stuff?
Yeah, that's a great question. So when I showed that slide showing the ocean carbon sink compared with the land carbon sink, it was thinking about the anthropogenic influence. So how much extra carbon we think the ocean is taking up because of the influence of human carbon emissions. And so our current understanding to date is most of that extra carbon that the ocean is taking up is being driven by these chemical and physical processes and less by changes in the biology. But a really important caveat here is that the baseline background of the total rate at which that biological pump moves carbon from the surface to the deep ocean is about the same magnitude as our total annual fossil fuel carbon emissions. So it's a big flux. And so if we perturb that system and we slow down the rate of the biological pump, it would lead to a really big feedback effect on global climate. And conversely, if these changes to ocean ecosystems actually led to an increase in the ability of the biological pump to sequester that carbon, it also could play a really important role in slowing down the rate of that carbon accumulation in the atmosphere. So we don't yet have good enough numbers to really well quantify that, but that's the reason that I focus on that in my research, because it could play a really important role going forward.
Great. Thanks,
Thank
Hilary.
you. Thank you, Hilary and Chris.
We'll address other questions later. Yeah, I'll hand over to Alyssa to introduce the next speaker.
Yeah, no, that was just a wonderful conversation. And I'm so glad that Chris asked that question at the end, because this interplay between physics, chemistry, and biology is really one of the themes that we want to address today. So we'll definitely talk about that more in the discussion with all of the speakers again at the end. So thank you, Hilary. One other thing that I really wanted to talk about at the end, so I'll just sort of put a pin in it for now, just to come back to later, is you just said, Hilary, something really important, which is that there aren't good enough numbers to actually make calculations and to make estimates. And I really want to talk about prediction and how good we are or how not good we are at predicting things that happen in the water, in the atmosphere, on other planets, et cetera, all together at the end. So we'll just remind ourselves to come back to that later.